Welcome to Pdborama. Tonight we will be investigating the Protein Data Bank. In the light of numerous retractions from the PDB and shocking revelations about the quality of some of the structures deposited there, we will be answering the question on everyone's lips: can we trust the PDB? We now go over to Eddie reporting undercover in the field at Diamond.
This is Diamond Sync Control. It's used by approximately 3,000 researchers every year in both academia and industrial uses. Of the PDB, 90% of the protein structures which have been solved were done by X-ray crystallography. But can this be trusted? Jonathan Harrison investigates.
The process of inferring the protein structure from the diffraction data relies upon taking a Fourier transform of the diffraction patterns, but phase data is lost. Extra data must be used to solve this phasing problem. We obtain an observed electron density map and must fit a model of a protein structure to this, which is where we introduce subjectivity dependent on the quality of the map. If 5 crystallographers were to refine the same data, they would all produce 5 slightly different models.
The blue mesh is an example of an experimental electron density map into which a model protein structure has been fitted. In this example, the model matches well to the experimental data. However, not all entries in the PDB show a good match between experimental and model density. The green and red mesh show an electron density difference map between experimental and model density. Green mesh shows an underfitted region where there is no model to match experimental density, while red shows an overfitted region where there is no experimental density to match the model.
One source of errors is the resolution at which data is collected. The resolution possible is dependent on the quality of the protein crystal, which is a particular problem for membrane proteins. At less than 1.5 angstroms, atomic details are visible. At around 3.5 angstroms, side chains start to poke through the electron density. And by the time we get to around 5 or 6 angstroms, only the main backbone is visible, and most of the rest of the details are obscured. If the refinement process is extended too much, artifacts in the model can develop due to overfitting. Each atom has 3 position coordinates and a B factor, indicating the degree of movement of the atom in the crystal. We have far more degrees of freedom in our model than in the data, thus overfitting is a constant danger. A well-publicized case of overfitting is the initial structure of an ABC transporter, which was built into the wrong-handed electron density map. Fortunately, the structure was subsequently redetermined via a homologous structure by Dawson and Locker 2006. The original paper was retracted from Science.
The risk of overfitting can be reduced by using known physical and chemical properties of protein structures to constrain the proposed models to scenarios which are physically plausible. I've got here an example of a section of protein. So this would be one residue, this would be its side chain, and then the rest of the protein would extend in both directions here, and this is the peptide bond connecting it to the adjacent residue from here. So the first constraint would be on the length and angle of the specific bonds in the molecule. So trying to fit, for example, this molecule here to something like this is going to be disfavored because this bond will be the wrong length for the data, and here you're putting strain on the angle of this one, whereas if we try to fit it here, that would be much more favourable. Another constraint is the requirement for the atoms not to sterically clash with each other. So if the atoms try to occupy the same space, that's going to be highly disfavoured. Linked to that is the concept of torsion angles, which is the angles of rotation around each of the bonds in the molecule. So starting with a peptide bond, which is the angle here is referred to as omega, and any deviation from a planar structure is highly disfavoured because the interaction between all 3 of these atoms are forming the bond. On the other hand, the phi and psi angles are much more freely able to rotate, but in reality they're constrained to specific configurations in order to avoid steric clashes between the protein side chain, the extending protein chain, and the carbonyl oxygen here. Another constraint is for the formation of hydrogen bonds between suitable donors and acceptors, such as the hydrogen here and the oxygen here. So if you already fitted data for an oxygen and nitrogen up here, then that would be favourable to then fit the rest of the protein to this structure here, which forms hydrogen bonds.
So can structures from the PDB be trusted? Fortunately, numerous validation analyses are undertaken before structures are deposited in the PDB.
Here we have an example of a Ramachandran plot. It describes energetically favourable regions in the backbone angles phi on the x-axis and psi on the y-axis. The pink regions are preferred, yellow regions are allowed, and grey regions are outliers. This plot was originally based upon empirical hard sphere calculations made by Ramachandran in 1963, but has since been updated to include data from other entries in the PDB. Although outliers are locally energetically disfavoured, there may be situations where they give a globally minimum energy.
Various software is available to assess a model's quality. For example, Phoenix is used to build a model from data and assess its quality as we go along. Other software available includes OOPS and WattCheck, as well as mole probity.
Another method of model validation is the R factor. This measures the discrepancy between the predicted electron density from the proposed model and the observed electron density from experiment. Good structures typically have R factor less than 20%, while a random collection of atoms could have an R value of around 60%. To avoid the risk of overfitting, about 10% of the data is typically withheld during the modelling process. An R-free value is then calculated by seeing how well this data fits to the model proposed by the remaining 90%.
It is not just electron density that can result in errors. Here we see a structure consisting of one dimer and two monomers. However, if this were regrouped, it could be presented as two identical dimers next to each other. This would make much more sense biologically.
Our hard-hitting investigation has left no stone unturned in our quest to discover the secrets of the PDB. We have found damning evidence of implausible structures and badly fitted models, leading to low levels of trust amongst respected academic communities. PDB apologists tried to thwart our progress, but we were not deterred.
Thankfully, the PDB has taken these criticisms into account, and now new entries have to pass rigorous checks to be able to enter it, and any failures have to be explained. The PDB publishes sliders on each entry, which gives a percentile which various metrics fall in compared to other X-ray structures and structures with similar resolutions. When using the PDB for individual entries, researchers should consider the accuracy of the data they are assessing by ensuring that these metrics meet the requirements of their study. For higher throughput computational studies, researchers should be willing to disregard data if it fails to meet case-dependent benchmarks.
So, to summarise, X-ray diffraction data does not give us a protein structure, but instead gives us an electron density map like so.
Building a protein model into an electron density map is a subjective process and contains multiple opportunities for error. Applying knowledge-based constraints can help limit the proposed models to feasible protein structures.
Validation tools exist which can score the quality of protein structure models.
So next time you want to look up a protein on the PDB, don't do it blindly. Think.
Guys, can we get a move on? It's really late. Next week on Pdborama, the SABS breakthrough. A place for all or just SABS? Find out.